Good evening, everyone. Welcome all to the problem solving session of NPTEL course on ice engines and gas turbines. Myself, Pradeev E, I am one of the TF for this course. Today, we will start with the basics of gas turbines. And before moving on to the gas turbines, we will just brush up some basics of thermodynamics first, and then move on to gas turbines. So, in thermodynamics, we have some terminology called system and surrounding. Here the system means the object or the matter that is of interest to us, and on which we will do analysis on. So it can be a piston with gas inside, or it can be a turbine which is turbine or pump which is taking in water and pressurizing the fluid and sending out. And so in this case the object of interest will become the system, and anything outside this will become the surrounding, and this system will be able to interact with the surrounding in terms of mass transfer or heat transfer. And we generally assume that the surrounding is large enough that there is no change in temperature because of any change in the change or heat transfer or work transfer from the system. So assume we add some electric heater to an ocean or to the surrounding air, room air, and since we assume in thermodynamics we make this assumption that the surrounding heat capacity is very high, that whatever we add the heat to the surrounding will not affect the ambient temperature or the surrounding temperature. And this system can be of two types in terms of mass, constant mass system or constant volume system. So an example for constant mass system is as I said, it's a piston with some gas inside, and if you it can be compressed or expanded, heat can be added or heat can be rejected from the system, but always throughout the entire process the analysis will focus only on the same mass of the system. And even though the volume changes, we are not interested in the change in volume, but we will focus only on what happens for the particular mass of the system. So this kind of system is called constant mass system, and we have something different system called as constant volume system. In this, so a typical example will be a pump or a turbine where fluid keeps going in, represented by m dot in, and fluid also goes out, represented by m dot out. Enthalpy with an enthalpy in and enthalpy out. But we are not focused on the masses that is coming in and going out. We are only focused on what happens within the constant volume. So in this volume, whatever happens is what we are focusing on. So here there can be heat transfer into the system, or heat transfer out of the system, or transfer in or out of the system, but we are only interested in what happens within this confined volume. So this is one type of classification, and another type of classification is in this we will have open system, closed system, and isolated system. In open system we can have heat and mass transfer. So one good example can be a bowl with water, and maybe it is heated up with the Bunsen burner or something, and now the system of the water in the beaker will get heat transferred into the system through the flame, and can also get the water can evaporate and go out of the system, and thus that way it can have mass transfer. And in closed system we will have only heat transfer, but not mass transfer, or you can say energy transfer, because there could be systems where we will put some mechanical work inside the system. So this could be like a system with a piston cylinder system, where you will apply some pressure and do some work on the gas, or the gas can do some work on the piston and so on, but you will not the mass inside the system will never come out. So this is closed system. And there is something called isolated system, where there is no energy transfer and no mass transfer. So this could be as an example would be a thermo flask. So we can fairly make an assumption that the flask there is no heat transfer in and out of the system, and there is no since it is a closed flask, there is no mass transfer. I hope this would be clear. If you have any questions, you can ask me now. Next, I will just talk briefly about the first law of thermodynamics, and also I will mention explain the sign conventions that we generally follow. So first law of thermodynamics is the law of conservation of energy. That means it states the energy can neither be created nor be destroyed, but can be transferred from one form to another. And here in this thermodynamic system, we say the energy can be transferred from the heat energy can be transferred as work, and vice versa. And the governing equation for the first law of thermodynamics is delta U, that is the change in internal energy of a system, is heat transfer minus work transfer. So here Q is generally stated as heat supplied to the system, and any heat supplied to the system is taken as positive, and any heat rejected by the system is generally taken as negative. And similarly for work is the work done by the system on the surrounding. By the system, and this is also taken as positive. So when the system does work on the surrounding, it is positive, and when surrounding is doing some work on the system, then it becomes negative. And the difference in this between the heat transfer and work transfer in any process will be the change in internal energy of the system. So I think till this things are clear, and earlier we have seen something called air standard cycle for auto and diesel cycles. That is I will just dot auto cycle. In auto cycle we had air compressed at isentropically, and then heat is added at constant volume, and then the gas is expanded isentropically, and then heat is rejected at constant volume. And similarly, I will mark this 1, 2, 3, 4. And similarly we had diesel cycle, where the compression is done isentropically from 1 to 2. The heat is added at constant pressure, and then the expansion takes place at constant entropy, and then heat is rejected at constant volume. So we have seen these kind of cycles which we call as standard cycle. And there is another dual cycle, which is a mixture of Otto cycle and diesel cycle, where the compression is done isentropically as in the previous cases, and heat is added in both constant volume for some amount and then constant pressure for some amount, and then it is expanded isentropically, and then heat is rejected at constant volume. So these are the as standard cycles that we have seen previously, but now we have something called Brayton cycle. So here as in the previous cases, the fluid is first compressed isentropically, and then heat is added at constant pressure, and then expansion takes place at constant entropy, and then heat is rejected at constant pressure. So now we have two pressure ranges, pressure limits or pressure levels in this cycle, and if we draw the same thing in TS diagram, we have this isentropic compression represented by a straight line, vertical line, because entropy is constant, S is constant there, and then we have heat added at constant pressure, which is represented by a curve like this, and then expansion occurs at constant entropy, and then the heat rejection happens at constant pressure. So this is as standard cycle for Brayton. Now there is something called closed Brayton cycle and open Brayton cycle. Here this we can assume something like the compression happens to a compressor. Air enters at state 1, and then after compression the air is taken out and fed to a combustor, where heat is added at constant pressure, and then it is expanded in a turbine. So this is compressor, this is turbine, and then it is rejected out to the atmosphere. So if it is just rejected out to the atmosphere, and without recycling the working fluid back, then it becomes open cycle. And in case of a closed cycle, this the air at state 4 is fed to a heat exchanger where the heat is rejected from the system and then fed back to the compressor. So depending on the working fluid, so if the working fluid is just air, then they generally let it out to the atmosphere and not having the then we can avoid having another heat exchanger and then sending it back. But in there are some gas turbine cycles which run on carbon dioxide or some other working fluid. So for those working fluid which are precious, then it has to be taken back. This is compressor, this is turbine. At state 4 it is taken, and there is a heat exchanger to reject the heat and then given back to the compressor at state 1. So these are the basics of the Brayton cycle. If you have any questions, you can feel free to ask now. If there are no questions, then I will move on to the next slide. Okay, then you can see the first problem. A gas turbine power plant operates on an ideal Brayton cycle, has a pressure ratio of 8. The gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the air standard assumptions, determine the gas temperature at the exits of compressor and turbine, the back work ratio and the thermal efficiency. So here we need to calculate the temperature at the exit of the compressor turbine, and they ask us to find something called back work ratio and thermal efficiency. So the expression for efficiency would be straightforward. Generally we call efficiency as desired work output or desired output by input. So in terms of in case of heat engines, it will be work output by heat input. In Brayton cycle we have work coming out of the turbine, but part of the work is again taken back for the compressor. So then we will essentially have the work output as turbine work minus compressor work and divided by Q in, that is the heat supply. So this is the thermal efficiency. And we have something called back work ratio. So this is we are getting some work from the turbine, but part of the work is given back to the compressor, and this ratio is called back work ratio. So that is compressor work divided by turbine work is called back work ratio. Now I think we can have the schematic. the temperature at T1 is equal to 300 Kelvin, and temperature at the turbine inlet, so that is at T3, it is 1300 Kelvin. We have told the pressure ratio is 8, that is P2 by P1 or P3 by P4 is 8. And utilizing the earth standard assumptions, we can calculate the exit gas temperature at the exit of compressor and turbine. So we know for the isentropic compression, we have this expression PV power gamma is equal to constant. Using this and using ideal state equation, that is PV equal to RT, so that is PV by T is equal to constant. Using these two expressions, we can derive the relation between pressure and temperature during isentropic compression. So here we have P1 V1 power gamma equal to P2 V2 power gamma, whereas here we will have P1 V1 by T1 is equal to P2 V2 by T2. Now I want to have expression between pressure and temperature, so that means I have to eliminate the volume from this expression. I can calculate V1 by V2 and substitute back in this equation in 1. So V1 by V2 will be P2 by T2 into T1 by P1. Yes. So putting it back here, I will have V1, so P1 by P2 is equal to V2 by V1 power gamma. So that is from here I can write T2 P1 by P2 T1 power gamma. Now if I take gamma on the other side, I would have T2 by T1 P1 by P2 is equal to P1 by P2 power 1 by gamma. So this will be T2 by T1 is equal to P2 by P1 P2 by P1 power minus 1 by gamma, and here T2 by T1 is equal to P2 by P1. Since it is 1 minus 1 by gamma, we will have gamma minus 1 by gamma. So I think this expression generally we will remember. It is better to remember instead of deriving, but I used to derive when I don't remember. Now T2 is equal to T1 into P2 by P1 power gamma minus 1 by gamma. Here T1 is given as 300 Kelvin. The ratio between P2 and P1 is given as 8, and we on the exponent we have 0.4 by 1.4. Since gamma is set as R, and we take it as 1.4. So this is 543.4 Kelvin. Now we need to also calculate the turbine work and compressor work at the later stage. So it is better to keep calculating the compression expansion work as we know the other parameters. So now so this compression work can be said as enthalpy at state 2 minus enthalpy at state 1, and this can be written as Cp into T2 minus T1, and we know T2 is 543.4 Kelvin and T1 is 300 Kelvin, and Cp is 1.005 kilojoule per kg Kelvin. We have 543.4 minus 300, so Wc is this is 244.62 kilojoules per kg. We don't know the mass of the system, so we will have everything in terms of per kg. So this is the compression work, and similarly during expansion the turbine inlet is given. With that we will be able to calculate the turbine outlet temperature. So that is T3 by T4 would be P3 by P4 power gamma minus 1 by gamma so T3 is known, so we need to calculate T4. That would be T3 into T3 divided by P3 by P4 gamma minus 1 by gamma. So here T3 is 1300 Kelvin and this ratio is 8 pressure ratio, and on the power we have 0.4 by 1.4. If you are also following with me, you can also try to answer this computations. Chaudhary, are you following the problem? You can solve it. Okay, so we have just T4 as 717.6 Kelvin. Now we know the temperature T3 and T4. With that we can calculate the turbine work. So turbine work is enthalpy at 3 minus enthalpy at 4, which would be Cp into T3 minus T4, and T3 is known, that is and Cp is 1.005 into T3 is 1300 Kelvin minus T4 is 717.6 Kelvin. So we will have the turbine work. So this is 585.312 kilojoule per kg. If you want to solve parallelly and then check the answers, you can let me know. If I have to wait, I can wait. So now we have calculated the temperature, gas temperature at the exits of the compressor and turbine. So that is at compressor exit we had 543 Kelvin, that is T2, and similarly at turbine exit we had temperature of T4 as 717.6 Kelvin. And we have also calculated the compressor and turbine work. Now we can calculate the back work ratio. So back work ratio is compressor work by turbine work, that is compressor work is 244.62 divided by turbine work is 585.312. So this is 0.418. Similarly, we need to calculate the thermal efficiency. So what back work ratio essentially says is, like, for every 1000 or 1 kilojoules that we have produced from the turbine, 0.418 times of that work will goes into the goes for compression, and only remaining is what we will have. So that means the net work output I would say it is W, that is turbine work minus compression work. This would be 585.312 minus 244.62. So this is 340.69 kilojoule per kg. So even though turbine produces 585, we would have only 340 after compression work is negated. Now we can calculate the thermal efficiency. Thermal efficiency is given by net work output by Q input. Here Q input we haven't calculated it, but it can be set with the temperature difference between T3 and T2. So Q in is enthalpy difference between state 3 and 2, that is we have Cp into 3 minus T2. Cp is 1.005 into T3 is given as 1300 Kelvin, and T2 is we have calculated. T2 is 543.4. So now we will have the total heat that is added to the system. This is 760.38 kilojoule per kg. Now we can calculate the thermal efficiency, which is 340.69 divided by 760.38. This is 44.8%. Do you have any questions? Okay, if there are no questions, I will move on to the next concept. So far we have assumed isentropic compression and expansion work from the compressor and turbine. That means we have calculated the what would be the temperature at the exit of the compressor or turbine when the input temperature is given, and also the pressure ratio is given, and we assumed that the entropy remains constant throughout the system, throughout the process, compression or expansion. But in real case, there would be some entropy addition to the system, entropy production, and because of this there will be the net work output of the turbine, or net work that has to be given to the compressor will be a little more than the ideal case. So we have compression work from this drawing on the right hand side. The bottommost the pink line represents a constant pressure line. This line is constant pressure line, and similarly when we compress from one to from pressure P1 from P1 to P2, when I compress at the constant entropy, I would end up in state 2s, but in real case there will be some entropy generation and I would end up in 2a. And these two process will these two states, 2s and 2a, will lie on the same pressure curve, but isopressure line, but the entropy will be a little higher and the temperature is also higher. So the compression work isentropic is here H2s minus H1, but in actual cycle WC actual is H2a minus H1, right? So that means this is more than the actual work input is more than ideal case. Now I can define the efficiency of the compressor, that is the isentropic work that has to be supplied divided by the actual work that is supplied to the compressor. So this is with the deviation from the ideal compression process, and similarly we have for the turbine process we have from pressure 3 we are expanding to pressure 4, and during this if we have expanded to in a constant entropy, we would have ended up in 4s state, and if you see the temperature difference, it is higher than the actual case where we have ended up in 4a. So because of this, ideally we should have obtained this difference in enthalpy, but now we are getting only this much enthalpy. So writing in expression, the turbine ideal case is in ideal case the turbine work will be H3 minus H4s, but the actual case we have only H3 minus H4a. Here this is less than the ideal case, and if you define the efficiency of the turbine, we would have the actual work output by isentropic work output. I hope this is clear. Then we will solve one problem using this efficiency. Assume a compressor efficiency of 80% and turbine efficiency of 85%. Determine the back work ratio, the thermal efficiency, and the turbine exit temperature of the gas turbine cycle discussed in the previous example. So in the previous example we had I would represent this in TS diagram. So we had compression at constant entropy, then we had constant pressure heat addition, and then we had isentropic expansion, and then constant pressure heat rejection. Now since the compressor is only 80% efficient and it is deviating from the ideal case, then it will go somewhere like this. So it will end up in 2S or 2A, and similarly when it expands, it will from 3, instead of vertically coming down to 4, it would end up in something like this, 4. So now we know the compressor for actual is efficiency of the compressor is isentropic work divided by actual work, and this is 0.8. Isentropic work is already we have calculated, that is 244.62 divided by actual work. So this so the actual work for the compressor is 244.62 divided by 0.8, that is 305.77 kilojoule per kg. So that means in the ideal case we should have supplied only 244.62 kilojoules of energy to obtain a pressure ratio of 8, but now because of its inefficiency we are supplying around 60 kilojoules more. Similarly, if you write the expression for the turbine efficiency, we will have turbine actual work divided by isentropic work. So this is 0.85 equal to actual is not unknown, isentropic work is what we have calculated as 585.312. So that means turbine actual work is equal to 0.85 times the 585.312. So this is 497.5 kilojoule per kg. So we have calculated the actual turbine work output and compression work input. With this we can again calculate the back work ratio, thermal efficiency, and turbine exit temperature can also be found. So the actual turbine compression work is 305.77 and actual turbine work is 497.5. This is 0.6146. So earlier we had around this value to be around 0.4. That means 40% of the turbine work is supplied back to the compressor. Now it is 61%. That means 61% of the work output from the turbine is supplied back to the compressor. Now we can calculate thermal efficiency. For thermal efficiency we need to calculate Q in. Now it is enthalpy 3 minus enthalpy 2A. So that would be I think before this we need to calculate the enthalpy at 2A. Say since this efficiency of compressor is 0.8, that means it is H2 minus H1 divided by H2A minus H1, or T2 minus T1 divided by T2A minus T1. Here only T2A is unknown. This is 0.8 is equal to T2 is we have calculated earlier 543.4 Kelvin minus T1 is 300 divided by T2A minus 300 again. This implies T2A is equal to 300 plus 543.4 minus 300 divided by 0.8. So that is 604.25 Kelvin. That means heat that has to be added will also reduce. Q in equal to H3 minus H2A. This is Cp into T3 minus T2A. That is 1.005 into T3 is 1300 or 1300 Kelvin minus T2A is 604.25. So this is 699.2 kilojoule per kg. With this we can calculate the efficiency. Thermal efficiency is W net divided by Q in. W net is turbine work minus compression work. Turbine work is 497.5 minus compression work is 305.77 divided by Q in, which is 699.2. This is 27.4%. So we have obtained the thermal efficiency of the actual cycle. And next is to find the turbine exit temperature. So this can also be found, like we have the turbine efficiency given, so that is actual turbine out divided by ideal turbine out. Here that is H3 minus H4A divided by H3 minus H4S, and turbine efficiency is given as 0.85, and this again we can convert to temperature T3 minus T4A divided by T3 minus T4S. T4S is what we have already calculated, and T3 is also known. T3 is 1300. T4S is calculated earlier. This one 717.6. Which means T4A is equal to 0.85 into 1300 minus 717.6. This will become minus and plus 3. So this is 804.96 Kelvin. So we have also calculated the actual turbine outlet temperature. Do you have any questions with this problem? Okay, if there are no questions, I can go to the next problem. A simple Brayton cycle using air as the working fluid has a pressure ratio of 8. The minimum and maximum temperature in the cycles are 310 and 1160 Kelvin. Assuming an isentropic efficiency of 75% for the compressor and 82% of the turbine, determine the air temperature at the turbine exit, network output and the thermal efficiency. So this problem is similar to the previous problem. We know in TS diagram the compression work, the compression process, which is isentropic, is represented by the vertical line, and then the heat addition at constant pressure will be a curve something like this, and then isentropic expansion is again a straight line, and then we have a constant pressure heat rejection. Here the minimum temperature is 310, so that means it should be T1. is T310, and similarly the maximum temperature is 1160 Kelvin. So that should be T3. I think the same thing can be repeated. Assuming this 2 and 3 to 4 are the ideal process, in actual process we will have something like this, ending up in 3A, and similarly the actual expansion looks something like this, and we will end up in 4A. Now, using the pressure temperature relationship, we can calculate the T2, that is ideal, the temperature outlet at the ideal compressor. So we know T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. Yes. So now we know T2 is equal to T1 is known, that is 310 into pressure ratio is 8 power gamma minus 1 by gamma is 0.4 divided by 1.4. So this is 561.5 Kelvin. Now using the expression for efficiency, we can calculate the actual temperature at the outlet. Compressor efficiency is given as ideal work input, that is H2 minus H1 divided by actual work input, which is H2A minus H1. So this can be written as T2 minus T1 by T2A minus T1. So then we have compressor efficiency is 0.75, which is equal to T2 minus T1 is 561.5 minus T1, that is 310 divided by T2A minus 310. So T2A will be 310 plus 561.5 minus 310 divided by 0.75. So this is 645.3 Kelvin. So this is the actual temperature outlet of the compressor. Now we can calculate the actual work input of the compressor, which is which is enthalpy difference H2A minus H1. This is Cp into T2A minus T1. This is 1.005 into T2A is 645.3 minus T1 is 310. This is 337 kilojoule per kg. Now we have calculated the actual compressor work input. We can similarly calculate the turbine work output. So for turbine work output we have T3 minus T4 is equal to P3 by P4 whole power gamma minus 1 by gamma. So that means T4 is equal to T3 divided by P3 by P4 power gamma minus 1 by gamma. Here T3 is known, that is 1160 given in the problem, and then P3 by P4 is 8, then on the power we will have 0.4 by 1.4. So this is 640.37 Kelvin. So this is T4 in an ideal case, but in actual case it would differ based on the isentropic efficiency. So we know efficiency of the turbine is turbine actual work output divided by ideal work output. So this is H3 minus H4A divided by H3 minus H4. This efficiency is given as 0.82 for the turbine, and this will become T3 minus T4A divided by T3 minus T4. So that is T3 is 1160 minus T4A divided by 1160 minus T4 is 640.37. So now we will have the value for T4A as 1160 minus 0.82 into 1160 minus 640.37. So this is 733.9 Kelvin. So turbine outlet temperature is calculated. Now we can calculate the turbine actual work. This is Cp into T3 minus T4A. This is 1.005 into 1160 minus T4A is 733.9. This is 482.2 kilojoule per kg. Now we have calculated the turbine work output and also the compressor work input in actual scenario. With this we can calculate the net work output and the thermal efficiency. For the net work output, is equal to WTA minus WCA. WTA is 482.2 and WCA is 337. Which is 145.2 kilojoule per kg. This is a network output, and next we have to calculate the thermal efficiency, and for thermal efficiency we need the Q in, that is enthalpy at 3 minus enthalpy at 2A. Enthalpy, this can be written as T3 minus T2A, and this is 1.005 into T3 is 1160 minus T2A is T2A is here 645.3. Now we will have Q in. This is 517.27 kilojoule per kg, and we can calculate the efficiency based on this, which is net work output divided by Q in. Net work output is 145.2 divided by 517.27. So this is 28.07%. So this is the actual efficiency of the gas turbine. If you have any questions with any of the problem, I would take it up for answering. Are you able to follow the problems?
No.
Yes, sir.
Okay, then I will go to the next problem. Air is used as working fluid in a simple ideal Brayton cycle that has a pressure ratio of 12, a compressor inlet temperature of 300 Kelvin and a turbine inlet temperature of 1000 Kelvin. Determine the required mass flow rate of air for a net power output of 70 megawatt, assuming both the compressor and turbine have an isentropic efficiency of 100% and 85%. Assume constant specific heat as output temperatures. Temperature at condition 1 is given as 300 Kelvin, temperature at 3 is given as 1000 Kelvin, and the pressure ratio P2 by P1 or P3 by P4 is given as 300, given as 12, and the power output is 70 megawatt. Now we will assume all 100% efficiency. this, we can calculate the temperature at the state 2. So now we know T2 by T1 is T2 by T1 power gamma minus 1 by gamma, that is T2 is equal to T1 is 300 Kelvin into the pressure ratio is 12 power 0.4 by 1.4. Can you tell what is the value of T2? Chandramanish, if you are also solving along with me, can you tell this value? Okay, so this is 610.2 Kelvin. And since they have told that it is 100% efficient, there is the isentropic and actual work output is the same, and also the temperature, everything will be the same for actual and ideal case. Now you can now we can calculate the compressor work. WC is enthalpy at state 2 minus enthalpy at state 1, which is Cp into T2 minus T1. Cp is 1,005 into T2 is 610.2 minus T1 is 300. This is 311.75 kilojoule per kg. So this is the compressor work, and similarly turbine work can be found out by finding the temperature at the outlet of the turbine, that is T3 by T4 is T3 by T4 power gamma minus 1 by gamma, which implies T4 is equal to T3 divided by T3 by T4 here. T3 is given as 1000 Kelvin, and P3 by P4 is known, that is pressure ratio of 12 power gamma minus 1 by gamma is 0.4 by 1.4. So that means T4 will be turbine work is calculated T minus WC, which is 510.94 minus 311.75. So this is 230.19 kilojoule per kilograms. Now our target is to have a power output of 70 megawatt. Equal to 70 megawatt. So that is 70 into 10 power 6 joules per second. Now for the mass flow rate of air is network output so mass of that air is network output divided by power output. Network output is 230.19 divided by power output is 70 into 10 power 6. In terms of joules, to have everything in the same units, we can convert the numerator also to joules per kg. kg per second. So 3.29 into 10 power minus 3. This is 3.29 times per second. Do you have any questions in the problem? And we can move on to the next section of the problem. Actually, I think here we had 230 kilojoule per kg. Section of the problem, we have the efficiencies of the machines given, which is 85% for both the case. So now the efficiency of the compressor is isentropic work divided by compressor actual work. This is 0.85 previous section, the m dot air should be power output by net output, right? Only then we will have here in terms of kg per second. Yes. That's what I was confused how the mass flow rate is very low. So now we will have power output by work output. This is 70 into 10 power 6 divided by 230.19 kilogram per second. Actually, we can substitute those units and then see finally what do we get. It's second per kg or kg per second. So we have 304.0.1 kilogram per second. Now we have actual compression work. This is 311.75 divided by 0.85. So that is 366.76 kilojoule per kg. And similarly, if you use the expression for the turbine efficiency, we will have turbine actual power output by turbine isentropic output, which is 0.85 is equal to W turbine actual divided by W turbine isentropic. So for the isentropic turbine output we have 510.94. So which means W turbine actual is equal to 0.85 times 510.94. This is 434.3 kilojoule per kg. And if you calculate the net work output, is equal to turbine work minus compression work in actual cases. Then we have 434.3 minus compression work is compression actual work is 366.76. That means overall we get 67.54 kilojoule per kg. So mass flow rate of air is power output by net work output. So that is 70 megajoules, that is 70 into 10 power 6 divided by 67.54 into 10 power 3. This is 1036.4 kilogram per second. Do you have any questions in this problem? we have a gas turbine power plant which operates on a simple Brayton cycle between the pressure limits of 100 and 1200 kilopascal. The working fluid is air, which enters the compressor at 30 degrees Celsius at a rate of 150 meter cube per minute and leaves the turbine at 500 degrees Celsius. Using the specific heats of air for air and assuming a compressor isentropic efficiency of 82% and a turbine isentropic efficiency of 88%, determine the net power output, the back work ratio and the thermal efficiency. So the two pressure limits is given for the Brayton cycle. If I plot the PV diagram, I have isentropic compression and then constant pressure heat rejection. This pressure is given as 100 kilopascal and the upper limit is given as 1200 kilopascal. The working fluid is air which enters the compressor at so T1 is 30 degrees Celsius, which is 30 plus 273, which is 303 Kelvin. And the flow rate, volume flow rate is given, which is 150 meter cube per minute and leaves the turbine at 500 degrees Celsius. So that means T4 is 500 degrees Celsius, which is 500 plus 273, which is 773 Kelvin. Temperature 1 is known and also the pressure ratio is known. Then using the expression T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. We have T2 is T1 is 303 into this is P2 by P1 is 12. On the power we have 1.4 by 1.4. This is 616.3 Kelvin. And now we do not know the heat added of the state at 3, but we know the state at 4. So again using the same expression T3 by similar expression T3 by T4, T4 is P3 by P4 power gamma minus 1 by gamma. We can calculate T3 as T4 into this pressure ratio, that is 773 into pressure ratio is 12, and on the power we have 0.4 by 1.4. And this is 1572 Kelvin. Consider the efficiency. We will have a different temperature of the work output. Since we are not asked to find the actual temperature output, I would first find the isentropic compression and turbine work and then calculate the actual work. So WC is H2 minus H1, which is Cp into T2 minus T1. Cp is 1.005 into consider the efficiency, which is for the compression, which is 0.8. We have isentropic work by actual work. So this is 0.82 is equal to 314.87 divided by actual compression work. So actual compression work is 314.87 divided by 0.80, which is 383.99 kilojoule per kg. Similarly, we can also calculate the turbine isentropic work and actual work. Turbine isentropic work is H3 minus H4, which is Cp into T3 minus T4. Cp is 1.005, T3 is 1572, and T4 is given, which is 773 Kelvin. So this is 803 kilojoule per kg. Now, using the expression for the turbine work, we will have turbine actual work output divided by turbine isentropic work output, which is efficiency for the turbine is given as 0.88. 88 is equal to turbine actual divided by turbine isentropic, which is 803. So turbine work actual is 0.88 into 830. This is 730.4 kilojoule per kg. Now we can calculate the net power output. Net power output is, or net work output. Okay, so since the volume flow rate of the fluid is given, we can calculate in terms of mass flow rate, and then we can calculate the power output. So it is 100. To calculate density, we have density at state 1 is P1 by RT1. So pressure at state 1 is given as 100 kilopascal, this is 100 into 10 power 3. For R we have 287, and temperature at state 1 is given as 303. With this we will calculate the density of the initial condition. So this is 1.15 kg per meter cube. So m dot is V dot into rho. V dot is 150 by 60 into rho is 1.15. This is 2.87 kg per second. Now second, and these terms in kilojoule per kg. So multiplying these two, you will get kilojoule per second. So this is 96 kilowatts. Next we have thermal efficiency, for which we need Qn. Qn is enthalpy at state 3 minus enthalpy at state 2. So that is H3 minus H2A. This is okay, we can calculate the temperature at 2. So we have compressor efficiency as H2 minus H1 by H2A minus H1. This is T2 minus T1 by T2A minus T1. For the efficiency for compressor is 82%. So 0.82 is equal to T2. T2 is 616.3 minus T1 is 303, and we have T2A alone is unknown. T2A is 303 plus 616.3 minus 303 divided by 0.8. So this is 685.07 Kelvin. Now we can calculate Qin, which is Cp into T3 minus T2A. T3 is calculated earlier, 1572. network output divided by Qn. Net output we have calculated earlier. We have calculated as power, so it is 730.4 minus 384 divided by 891.36. This is 38.86%. But I think we haven't matched the values given in the book. Did someone find where I went wrong? If you have any questions in this problem, you can ask me now. I think the next problem is pretty big. We cannot solve it in this time. So if you have any questions, you can ask now, or I think we can close the session. This next problem we can see in the next class. Thank you for participating. We will see you in the next class. Thank you.
Thank you, sir.